So, our last section of Unit 6, woo, which is also the first section of Unit 6. It's very, but, slope fields. Okay, so, synonyms. Okay, these all mean the same thing. If I say anti-differentiation, anti-differentiation. Anti-differentiation means the same thing as solve a differential equation. Okay. Means the same thing as indefinite integration. Indefinite integration. Those all mean the same thing. Okay. Now, we worked with differential equations. First of all, we worked with them at the very beginning of the semester, where you just had like f prime of x equals something, and you took the antiderivative to get, in this case, like x cubed plus 3x plus c. Okay? And then Tuesday, we talked about separable differential equations, where you have x and y, you get the x's together, get the y's together, you go through it. Okay? As I mentioned on Tuesday, that's not always going to be able to happen. Okay? For instance, dy dx equals x plus y. You can't separate those variables. You can't divide, multiply things to the other side to get dx with x and dy with y. Okay? So, we have what's called a slope field to help us visualize the graph of the solution to a differential equation. Okay? So, a slope field is a graphical general solution to a differential equation. Okay, we're going to graph it. Okay. And you can see on the different pages of your notes, I have all these graphs with these little tick marks, right? Okay. We are going to represent something in all those little check marks. Okay. I have no idea what happened to when this got copied, but it's going to keep you awake this morning. Okay. And pay close attention. It does. It does. I think it also looks like a wind map. All right, so we're going to start out with a differential equation that we know what the answer is, okay? Because it'll help us visualize what's going on. So if I say dy dx equals x squared, what is that literally telling you?
The slope of the original equation is x squared.
Is x squared? Yes, yes. The slope is x squared for all xy coordinates. Okay? So what we're going to do, we're going to take each coordinate, we're going to plug it into our differential equation, and we're going to figure out what the slope is. For example, for our coordinate 0, 0, dy dx, when we plug in x is 0, y is 0, we get 0. So at 0, 0, we're going to make this little itty bitty tangent line with slope 0. at the coordinate 0, 1. When we plug x is 0, y is 1 into dy dx equals x squared, what do we get? What do we get? If x is 0 and y is 1, say louder. X is 0. We have x squared.
0.
Is there somewhere for me to plug in y? So does my y coordinate really matter right now? No. So at 0, 1, we have a slope of 0. Okay? At our coordinate 1, 1. I don't know why I chose 1, 1. At our coordinate 1, 1, 1 squared is 1. So a little tangent line of 1. Okay? See what's happening here? Okay. Do we have to write all this down? Oh, God, no. Okay? Let's just go. Let's talk about it now. The coordinate 1, 0. When we plug it in, would have slope of 1. Okay? Let's go over here to 2, 0. 2, 0 would have slope of 4. So this is going to have to be pretty steep. Okay? What about 2, 1? 4. Basically, anytime x is 0, we're going to have slope of 0. Anytime you have x is 1, we're going to have slope 1. And anytime x is 2, we're going to have slope 4. Okay. All right, let's go over here to the coordinate negative 1, 0. What is our slope going to be? When x is negative 1, y is 0. It's going to be 1. X squared, negative 1 squared is 1. Same thing at negative 1, 1. Our slope, x squared, is 1. Negative 1, 2. X squared is going to be 1. The coordinate negative 1, negative 1. X squared will be 1. And then over here, negative 2, 0. dy dx equals x squared would be 4. Negative 2, 1. X squared would be 4. We're all very distracted right now. Okay. Okay. Look at those little bitty tangent lines. If you follow, see, I think this looks like wind. Have you ever looked at like wind maps, like for weather? Okay, if you follow the wind, what if and like you connected? Ooh, what do those look like? They look like cubic functions. And why would they look like cubic functions? What?
That's the OG function.
That's the O. Did you say OG?
I don't know.
Like original?
Yeah.
Our original function would be cubic, right? If our derivative is x squared, when we solve this, we get 1/3 x cubed plus c, right? So all of these look like cubic functions, and you notice how we're representing a lot of different cubic functions here? It's because of that plus c. Okay, we can have a cubic function at any height, which is why we see so many cubic functions there. Okay, so it's basically giving you the trend for the solutions, multiple of them, to your differential equation. Yes?
If they're all from the same line, if they're all from the lines. Like I have mine on the right side.
That would be incorrect, because when we plug in -1, up here we would have actual 1. Okay, so that doesn't be different. Yes? Well, that's going to be where you have a horizontal tangent. Yes. Yes. Okay. All right. Here is, well, oh, for crying out loud. It's not working out very well. Okay. Let's go to this one. This is the example that I gave you earlier. Okay? dy dx equals x plus y. This cannot be separated. We cannot solve this with the tools that we have in our toolbox. So the only thing we can do is represent it as a slope field. So I'm going to give you some time to determine what each of these slopes would be. For example, if I am at the coordinate 1, 2, x plus y would give me a slope of 3. dy dx is, I guess y prime is what they are calling it. Same thing. Y prime is 3. Okay, if I'm talking about the coordinate -1, 1, y prime would be 0. Okay? Go ahead and take some time to draw out all of those little bitty tangent lines. I'm hoping you catch on to maybe some patterns as you're going through this, right? Okay, pick one. Okay, so here we have 1, 2, x plus y, I get it equal to 3. So here we go, which is 3. Do you see some like diagonal patterns?
Yeah.
Okay. I have my slope field up here for you to look at. negative 1, 0, negative 2, 1, negative 3, 2, 0, negative 1, 1, negative 2. You notice how those are all the same? If I connect them, okay, there's an asymptote. Okay, if you can connect a line with your slopes, there's an asymptote. Okay.
Wait, at well, like at what line? Like what line is that? It like on the original graph.
This right here.
Oh.
Okay. Now, here it's giving us an initial condition, 0, 1. Okay. So 0, 1 is where? Right here. Put a coordinate there. You know, at 0, 1, the slope is a positive 1. Okay? We need to draw the solution. So basically, you need to follow the wind. Where does the wind blow you through this slope field? I know that sounds super cheesy, but that's the best way I can describe it to you. Okay, right now we have a slope of 1, and we know it has to start getting steeper. Okay, here I'm going to follow my slope of 1, but I know over here we have to have a slope of 0. So somewhere here it's going to have to change directions, and then I have this asymptote that we have to approach. So do you see along this line here they all have slope 0? So I know that when I kind of hit that, I'm going to have a slope of 0 and then approach that asymptote. Okay? You're probably only going to go through one little tangent line. Okay? And then the rest is just going to be kind of throughout. Okay? It's not necessarily connecting the dots. It's taking one dot and following the trend. Does that make sense? Okay. Questions before we move on? Awesome. All right. Okay. So here I have slope fields and potential general equations. Okay, so when I'm looking at these slope fields and I have the general equations, let's go back up here real quick. And I realize that I don't have mine on here. But with this slope field, what was our general equation for this slope field on the front page?
1/3 x cubed.
Y equals 1/3 x cubed, right? And what did our slope field look like?
Like cubed.
Okay, so I'm going to give you about a minute to discuss at your pod the answers to this example with the two slope fields and multiple possibilities for general equations. Go. Neither, neither,
Yeah.
All right, everyone together. Pod 4, you're going to help me out first. Okay. Number one, Pod 4, what did you label that as?
I did number 2 first.
You did 2 first? Okay, so I will let you answer number 2. What? D for number 2. D for number 2. This looks like a cubic function that's really, really well, I can't even think of the word, but looks like a cubic function. Do you agree? Okay, I know that these looks kind of vertical. It's because the technology isn't super awesome and those are just super duper steep. Okay, but they're not actually vertical. Okay. Okay, good. So number 2 is D. Okay. Part 1, what do you think about slope field number 1?
Susie.
Okay, Callie says sine, Trevor says cosine. Callie, why do you say sine?
Because it's a sine wave.
Because it looks like a sine wave. And why do you say cosine?
It starts. I think it starts with the top.
Okay.
Oh, yeah.
Trevor? You think it's sine? Okay. It is sine because we can see that sine wave and it's starting with that 0, 0 with that nice slope. Okay, to do that. Now, if I gave you like dy dx equals cosine, it would be a different story. Okay? If dy dx is cosine, then this would be our graph. Okay? Which brings me to our next set of mapping. Okay? Now I am giving you the differential equation. And you need to match their slope fields. Okay? So like this one here, dy dx equals xy. If I plug in the coordinate 2, 1, I get a slope of 2. If I plug in the coordinate 0, 5, I get a slope of 0, etc. You need to figure out which slope field matches the differential equation. So it's not as simple as what does it look like. You have to think a little bit, look for some patterns. I'm going to give you about 2 or 3 minutes to really go through this one together with your pot. Okay?
The first one is the last one.
It does, it's so slow, yeah, it's fine. Actually, it's like B, right? It should be B. We should use 3.
I was asking
Oh, wait, or is it 3?
All right, everybody back together. All right, let's go through each of these. Pod 1. Number 1 matches with which picture?
Sorry.
Number 1 matches with F. Catherine, why?
because it's the graph and the
Okay, what's the antiderivative of e to the x? E to the x. So that was messed up, right? Okay. Number 2, what? X over Y. Pod 2, what does it match with? So this matches with 1. Number 2 matches with E. Okay. Michaela, why does 2 match with E? Like, what did you notice that led you to the asymptote? Okay. We have like a diagonal pattern happening, right? So, hold on. What happens when we divide by 0? You think 2 should go with C instead? Can you explain your reasoning, Jackson?
Because like the x over y is going to equal 1 along the line with y equals x. And for e, the slope is 0, but for c, the slope is 1, which is what it should be.
Okay. Do you also notice how all of these are vertical? Anytime we divide by 0, we get an undefined slope, right? Well, anytime y is 0, we're dividing by 0, which means we're getting an undefined slope, okay? So that's another characteristic that I would really look at, okay? Pod 3, number 3. 2 minus y is a, okay? Eli, give us what stood out to you there?
Because for y equals 2, the slopes are all 0, and 2 minus 2 equals 0.
Okay, for y equals 2, the slopes are all 0. Also, do you notice how this solely depends on y? So everything is like a horizontal pattern, right? For that very first one we did, it solely depended on x, and so we had like columns of the same slope. Good. Pod 4, number 4. What stood out to you there?
Same thing you said about A, except it's vertical patterns instead of horizontal.
Okay, you had the vertical patterns. Something else that sticks out to me, like I know the antiderivative of x is 1/2 x squared, right? So I see a parabola, I know it should go with a linear differential equation, right? Okay, pod 5, number 5. Okay, Chris, what stuck out to you about E? Okay, we have like that diagonal pattern, right? When x and y are the same, you have like those 0 slopes, right? And then you have that asymptote happening. So by process of elimination, D is 6, which I think a lot of you actually identified first, right? That graph looks like negative cosine, and so it goes with the sine derivative, but it's also, you only trig 1 up there, so it was easy to identify, right? Okay. We have 10 minutes left. Let's go to that last example. Okay. On the axis provided, sketch a slope field for the given differential equation. Okay? We're going to sketch a slope field. So we have x times y over 2, which means anytime x is 0, we get 0 slope. Do you agree? Anytime y is 0, we get 0 slope. So then just bear with me here. We have like a 1/2 slope, 1 slope, 3/2 slope right there. We have a slope of 1, slope of 2, slope of 3. Here we have slope of negative half, slope of negative 1, slope of negative 2. I'm just trying to get to the rest of it, okay? Here we have a slope of positive 1/2, positive 1. Here we have a slope of negative 1/2, negative 1, negative 1, negative 2. Okay. Now, we did all that work, but I don't think they actually make us find anything, do they? Okay, so I'm going to have to erase it so I have room, okay? I have to come down here. Part B. Write an equation for the line, for the tangent line to the curve y equals f of x through the point 1, 1. Okay, point 1, 1. What is our derivative value there? dy dx evaluated at 1, 1 gives us, did you say 1/2? Okay, so our tangent line equation, y minus 1 equals our slope times x minus 1. That's our tangent line equation. Now, use your tangent line to estimate the value of 1.2. All that means is we are going to plug in 1.2 for x. And we don't need a calculator, we can do this. 1.1 minus 1, excuse me, 1.2 minus 1. 0.2 times 1/2, 0.1. Our estimate is 1.1. Okay, we can't actually find the, well, actually, without finding the actual equation of the differential equation, we can use the tangent line to approximate close to the tangent line. Now, in part C, they actually ask us to find the solution to the differential equation. So, I don't know why I don't have very much room. I'm really sorry. We have dy dx. Is it xy over 2? Okay. So if we separate our variables, we have x over 2 dx on the right side and 1 over y dy on the left side. So I'm going to push through this. I would love to ask for your help, but we're just going to get through it, okay? So the antiderivative over here is the natural log of the absolute value of y, and the antiderivative over here, we have 1/4 x squared plus c. When we actually solve, we get y equals c e to the 1/4 x squared. Okay. Now, we know our initial condition of 1, 1, so we can actually plug in 1 for y and 1 for x. We get a c value of e to the negative 1/4. So when we plug it back in, right, we get y equals, our c value is e to the negative 1/4 times e to the 1/4 x squared. And remember, I'm going to want you to actually simplify that down. And I'm sorry that I'm kind of running out of room. But we're going to have y equals e to the x squared minus 1/4 is probably how I would write it. Just making those, adding those two fractions together. Yeah. Okay. Now, it is going to ask you to plug in 1.2. I don't want to worry about that right now. I really want to talk about part D. Before we actually plug in 1.2, is our estimate in part B an underestimate or an overestimate compared to what the actual value is going to be? Turn to your neighbor and tell them, under or over? Okay. Joe, you're pretty confident in an answer you had back there. What did you say? And why underestimate?
Because tangent line 1 is basically the C, actual equations.
Okay. I don't know if that's always going to be the case. Fail-safe way to think about it, look at your slope field and go to 1, 1. Concave up or concave down? Concave up. We have concave up at 1, 1, which means that tangent line at 1, 1 is underneath the curve. So it's going to underestimate your value. Okay? That's the way I want you to think about that. Okay? All right. Worksheet. 45. Yeah. So here's the deal. I understand that we went through 2 days worth of material in one, and you only have one night to do your homework. Now, you did get halfway through, would you say halfway through your book assignment? Okay. These slope fields, in my opinion, should not take you very much time. So I would definitely focus your time on slope fields since they are more new to you than exponential growth and decay. I'll check homework both days. I expect you to have some of each assignment done tomorrow, but I will give you the grace period of by Monday you need to complete both assignments fully. Do I think that you have time to complete both assignments tonight? Probably, but at the very least, you've already done some of the exponential growth and decay. Do some of this, and then by Monday for sure you need to have all of it done. Okay?
Yeah. I'll be gone tomorrow. So he's going to give me the
Yep.
tape